This is where it all begins. Every topic in FRCR physics traces back to what you learn in this lecture. Welcome to the masterclass. Once these core principles make sense, the rest of the syllabus becomes a matter of deduction rather than memorization. Before we start memorizing equations, why do I need to know about electron shells just to understand X-ray images? Because medical imaging is the art of inferring anatomy from radiation interacting with tissue. The image you see on the monitor is the direct result of subatomic collisions. Understanding radiographic contrast, managing patient dose levels, and predicting tracer behavior is only possible if we first understand the anatomy of the atom and the energy holding the nucleus together. We start with the atom. It is overwhelmingly empty space. The mass is concentrated in a dense cluster of protons and neutrons at the center. Think of the nucleus as the center pitch of a massive stadium. The electrons do not float randomly. They occupy distinct energy shells, labeled K, L, and M. The occupancy is strictly limited by the rule of 2n squared. The front row holds 2, the next holds 8, and so on. The K shell, the very front row, sits in a deep potential well. Removing an electron from this shell requires specific energy to overcome the nuclear pull. We call this binding energy. As you add more protons to the nucleus, increasing the atomic number, that binding energy increases. Iodine and barium are chosen because their K-shell binding energies, 33 and 37 keV, fall within the diagnostic X-ray spectrum. This alignment is the prerequisite for the interaction that produces high image contrast. That interaction is the photoelectric effect. If an incoming photon has energy equal to or slightly greater than the binding energy, it can strike an inner electron and eject it. Think of it like a cue ball sinking a target on a billiards table, leaving an empty pocket behind. An outer shell electron instantly drops down to fill that inner vacancy. That drop in energy levels releases a secondary photon, a characteristic X-ray, or it ejects a second electron, known as an Auger electron. MCQ 1.3 tests this relationship. To increase the binding energy of a K-shell electron, you need a stronger nuclear pull. The correct answer is B, increasing the atomic number. Radiation exists on a continuous scale. On this piano keyboard of energy, radio waves are the long, low-energy bass notes on the left. X-rays and gamma rays are the high-frequency treble notes on the far right. Frequency is the only physical difference between them. Electromagnetic radiation travels through space as a wave, but when it interacts with tissue, it strikes as a discrete, zero-mass particle called a photon. Max Planck unified this behavior with a simple relation: E equals hf. Photon energy is directly proportional to its frequency and inversely proportional to its wavelength. Short wavelengths mean high frequency, which dictates high energy. As these photons travel outward, the beam spreads. Beam intensity drops off rapidly following the inverse square law. Intensity is proportional to 1 over the distance squared. For the FRCR exam, remember the limitations. This mathematical drop-off is only exact if the source is a geometric point, and there is absolutely no scatter or attenuation between the source and the detector. MCQ 1.7 applies this geometry. Doubling the distance from a point source increases the square distance by a factor of 4. The intensity at the new position is quartered. We shift now from the electron shells to the nucleus. Because protons are all positively charged, they experience massive electrostatic repulsion. Left alone, they would tear the nucleus apart. The nucleus is held together by the strong nuclear force. It is a powerful short-range attraction between all nucleons that only operates at distances of about 1 femtometer.
This is the Segre chart, plotting neutrons against protons. Stable elements form a narrow band called the line of stability. Notice it bends upward past an atomic number of 20. Heavier nuclei require extra neutrons to buffer the proton-proton repulsion. Any nuclei that falls off this line is unstable. Radioactivity is the spontaneous transformation of an unstable nucleus attempting to reach that line. We measure this activity in becquerels, 1 disintegration per second. In a clinical setting, activity drops via 2 independent processes. The physical half-life is a fixed property of the isotope. The biological half-life is the time for the body to excrete the tracer. We combine these to find the effective half-life. Because these processes act in parallel, their rates add together. This means the effective half-life is always shorter than either individual component. Look at MCQ 1.10, a physical half-life of 6 hours and a biological half-life of 3 hours. 1/6 plus 1/3 equals 1/2. The effective half-life is 2 hours. How a nuclide decays depends on its position on the Segre chart. Unstable isotopes shed mass or charge to reach the central valley of stability. Isotopes above the line are neutron-rich. They undergo beta- decay, converting a neutron into a proton and emitting an electron. This moves them down and to the right on the chart. Isotopes below the line are proton-rich. They undergo positron emission, converting a proton into a neutron and ejecting a positively charged electron. This moves them up and to the left. Emitting a positron requires energy. The parent-to-daughter gap must be at least 1.022 megaelectron volts to create the electron-positron pair. Below that threshold, the nucleus must use electron capture instead. When a positron is emitted, it soon collides with an electron. Their combined mass is converted into two 511 keV photons, traveling in exactly opposite directions. This annihilation is the physical basis of PET imaging. For conventional imaging, we want to avoid the particulate emissions of beta decay, which dump kinetic energy locally into tissue. We prefer isomeric transition, where a metastable nucleus simply drops to a lower energy state and emits a clean gamma photon. This brings us to technetium-99m, the reference standard for diagnostic imaging. It possesses a specific set of physical advantages: a 6-hour half-life, a monoenergetic 140 keV gamma ray, and pure isomeric transition. Logistically, it is much easier to handle than PET isotopes. While those require the industrial scale of an on-site cyclotron, technetium-99m is eluted daily from a portable molybdenum-99 generator. That decay profile is the focus of MCQ 1.14. The reason technetium-99m is so well suited for gamma cameras is answer C. It's decay by isomeric transition, producing a 140 keV monoenergetic gamma ray. 5 critical laws to remember. 1. Atoms are discrete energy systems, and selecting materials based on K-shell binding energy creates radiographic contrast. 2. The E equals HF relation connects the wave to the penetrating photon. High frequency is the requirement for high energy. 3. The inverse square law is the mathematical basis for radiation protection. Doubling distance reduces intensity to 1/4. 4. The Segre chart governs whether a nuclide will undergo beta, positron, or alpha decay to reach stability. 5. Technetium-99m's pure isomeric transition is why it remains the benchmark for maximizing image signal while minimizing patient dose. The connection between these atomic principles and the clinical images we see is much clearer now. This was Lecture 1 of the RadSound Basic Radiation Physics Masterclass. See you in the next one.